I'm sure Paul's got ready to go. Ours is so hot, and you didn't know it.
Okay, Steve just called at me and said he couldn't be here this morning. So we'll just keep going from where I was.
Tuesday, 7:45. Actually, I think it was 7:43
or something. Last time we added the mixing box and an economizer control. And we just, at this point now, we were using outside air to condition, as air conditioned air, whenever it was available. Any questions on that? We went through it real fast, but any questions on how that worked or why we do that?
Whoa. Start over.
We also talked about hardwiring of those safeties. Does everybody understand the difference between hardwiring a safety or software interlocks? Anybody not understand that? I don't care if you say
I don't.
Do you not?
No.
I mean, right here we're talking about hardwired safeties. Okay, these are devices that here's your low temp detector, your differential pressure switch, the high static switch, the fire alarm. There may be others that are thrown in there, but these safeties are tied directly to a source of power. Power is series through those, tied directly to the device we want to shut down. Okay, as long as we have power from the transformer up here at the top, and these safeties are made, then the interlock relays over here are going to be pulled in, allowing the device to run. If any of these safeties trip, it's going to shut the unit down regardless of what's going on over in the software in our controller. Okay, we could shut our panel down. We could override software points. Those hardwired interlocks are always going to shut the unit down. Okay, as opposed to a software interlock that we might do through programming. Some people don't want hardwired interlocks.
Who's that?
Right here where we're picking up this digital input, that tells us that that low temp detector is tripped. That's all they want. They want the computer to see that that thing is tripped, and then the digital output going to that fan or whatever it is. Right here, over in this panel, we're going to do the logic that says, if this trips, turn this off. Okay? That's a software interlock. That relies on the panel being up, running, and the programming being correct, and nobody having overridden any of the points.
Does that include loss of power? Does that need to be emergency power then, or
Well,
is that all incorporated in the logic?
it just depends on how detailed you want to get. I can hook these up, like right now, this is hooked in a common and normally open. So if we lose power to this controller, what's going to happen to those contacts? They're going to switch it's going to switch over here to the normally closed, and our circuit's not going to be made to the enable point anymore. So if we lose power, the fan's shutting down. Okay? So now the other thing you might do, you might decide you want to put all these on emergency power, UPSs, so that they're up and running all the time. It just depends. But you know, when you start talking about power failures, though, you start figuring, does the air handler even have power anymore? Is it going to run? Well, regardless of what I'm telling it to do, is it even going to run? So,
Same way with loss of communication?
Yeah.
Do it through software?
loss of communication, you're just looking at different things that may fail. You know, these points right here don't really depend on any kind of communication other than that wire connected directly between them. They're not dependent on our communication between different panels. Okay, all that programming is done in this panel where these points are tied.
So whether or not you've got communication or not, once you've got a program in, it's going to relay.
Right.
It doesn't matter.
Right. As much as possible, we make things stand alone in their own panel. All these points that are tied in this controller have their point information and their program logic information in that panel. The only thing the communication's doing is feeding that information back to me so I can see it on a graphic front end somewhere. Or maybe I can do some more sophisticated system-wide control that's not critical. So if I lose communication, then that, you know, more sophisticated logic is critical, and it doesn't matter if I lose that. Okay? So software interlocks or hardwire interlocks. Good enough? I mean, is it? If we have another thing on these software connections here, over at the drive, you have some similar instances with starters. See, I have specific terminals here labeled safeties, and I have a specific terminal labeled start-stop. You know, that drive's going to act differently whether these are made or whether this is made. Okay? I may have the start-stop enabled, but if those safeties aren't made, it's not going to run. So if I do all software interlocks, I have to either jump this out or program the drive to ignore it. On a starter, just a plain starter with an HOA switch on it, do we tie our safeties in the circuit where it kills it in hand and automatic, or do we tie the safeties only into the automatic side? What do we normally do?
Just on the other side.
On the auto side, if you won't run it unmanned, you can, right?
What happens if somebody down there working on it, and to work on it, they put it in hand, and before they leave, they run off and forget about it and left it in hand? 3 months later, it's still running in hand. Okay, that again may be a customer-specific thing.
It sounds like it with most of the buildings that we go to anyway.
If,
Already running in.
if I'm designing it from scratch and I don't know the customer, I'm gonna wire those safeties to where it kills it in hand or automatic, so that it will not run in either position. If I know my customer and I know there's somebody that wants to be able to go down there and troubleshoot by putting it in hand, regardless of whether the safeties are made or not, I'm gonna leave that up to him. Okay? Let's jump over now to, if you still have them, brought them with you, the sheets that have the VAV box controller on it. Okay. Now, where are the VAV boxes?
In the ceiling.
In the ceiling, okay. VAV boxes, what are we using control on with the VAV box? What are we controlling? What's the VAV box serve?
Zone or
Individual zones or rooms, okay? As opposed to air handlers serving system-wide areas, the air handlers are sending the air out to the VAV boxes usually, okay? Now we're going to talk about the VAV box itself, how it's controlled. This right here is just a little diagram, a little quick drawing that basically shows how this is going to, how this controller is going to work in a real concise little fashion. It just basically, here, going from here across the bottom is your room temp. Going this direction, it's getting hotter. Going this direction, it's getting colder. So it says that at our cooling set point, there's a little dotted line here, it's hard to see. As we come down, as the temperature comes down to our cooling set point, this dark line here represents our supply air. Okay, this dark line just says we're going to start modulating the airflow down to some minimum airflow set point. Okay, as the room temp goes back and forth around this cooling set point, our airflow set point is going to go up and down. Okay, we're going to, as the room keeps getting cooler, we're going to stay at this minimum air. And what's this represent? This dashed line? This is our reheat valve. Okay, as we get down to our heating set point, which is this dotted line, we're going to go from valve closed up to the valve maximum open. Okay? Quick and dirty, simple little diagram. Doesn't tell you a whole lot, but I mean that's the basic, the basic theory of the VAV box. That right there has been true for years, even with pneumatics. Okay, with DDC now, we can take this and change it up, do just about anything up with it we want to. You have a cooling set point, heating set point. You might have different heating and cooling set points for daytime and nighttime. You might have a set point dial on your thermostat down here. Maybe those are the same point. Okay, so now we got, let's say we might have one dotted line here in the middle. And as our box goes down to minimum, our reheat valve starts opening up right away. Okay, so that's just a little, in a nutshell, how a VAV box works. Now, looking at this diagram down here, this is a representation of our VAV box. We have air coming from the air handler entering this side. We've got some kind of airflow pickup. Most of the time it's what we call either a flow cross or cross flow. Those are specific terms for different manufacturers. So that's some kind of airflow pickup. Right here is our variable volume damper. and we're showing we've got a damper actuator tied to that damper. Next, this expanded area here is just some kind of sound attenuation box. I mean, I don't even know why they still why that's in there, because it really doesn't have anything to do with the control of the box. Reheat coil with a valve and the piping associated with it, and then a supply air temp sensor that just tells us what temperature air we're putting out. Up here, this is our representation for the room thermostat, just like the one on the wall back here. In here, we've got a set point, possibly. We've got the room temp pickup. We might have an override button. We might have a display. Okay, for Siemens, those are all different options. We can either have them or not have them. This temperature sensor now sends the temperature through a wire, usually, maybe wireless, but sends the temperature to this controller, and it starts doing all the thinking, figuring out what it wants to do with the outputs. All the logic is built into this controller. You can put that on the wall by itself, hook the thermostat to it, hook up your actuators, tell it what kind of application he is, and it'll sit there and control without communicating. Okay? Right here, we're just showing a 24-volt power connection. This is our terminal strip that has our outputs and inputs going to the devices. This is a communication trunk so that we can read that information back at a central location. So the first output we have on here is our damper actuator. And most actuators can run 0 to 90 degrees. How much does it take to open or close this fully? The last one you hooked up.
How much what does it take?
How much rotation does it take to open or close that damper fully?
Depends. Some of them 45, some of them 90.
Yeah, all of them, there's about 3 different scenarios. Some of them, the damper is in there and has to go, it's straight up and down, it's fully closed. Straight across, it's fully open. So that'd be a 90-degree rotation. Okay, that fits perfectly with our actuator that does 90 degrees. Some of them are in here like this, where that's 45 degrees. You travel 45 degrees, it's full open. Now the trick with a lot of these is that they will continue on and travel the other direction and close off. So if you let that damper actuator travel 90 degrees, you actually go from fully closed, open, back to fully closed again. Okay, we've got to know that when we're setting that TEC up. Some of them actually have a 60 degree where they're sitting in there. They're weird, but you don't see those very often. Normally it's either 45 degrees or 90 degrees.
Is there an advantage one way or the other, as far as just the box goes?
Anybody know if there's an advantage? I don't.
It's better to keep it 90 if they're 90 degrees, because most people don't.
Yeah, for us, it's better for it to be 90 degrees because we're going to have less chance of screwing up. Control-wise, I don't know if there was an advantage in the past with pneumatics. Maybe it was easier to control 45-degree rotation than it was a 90. I don't know. But if we run into a 45-degree one, there's a place in the controller, you tell it it's a 45-degree rotation. So it knows that once it's traveled 45 degrees, it's fully opened. But it's incumbent on us to put that in there and then make sure that that actuator is tied onto that damper shaft correctly and set up to travel the right direction, or we're going to wind up overdriving it and going the wrong direction. Before you know it, we're closing it instead of opening it. The airflow pickups. Every VAV box, almost every one you see in the world today, is going to have some kind of cross-flow sensor that's going to give us an indication of the velocity pressure. Okay? velocity pressure, we can take that into an equation and calculate the CFM. That's what we need to know in order to make this controller work right.
Thomas, is there anything special about that cross flow sensor? I mean, if the one in the VAV is messed up, can you just add another one later?
You can buy aftermarket ones and put in there.
Does it work just the same?
They work, they all do the same thing, but airflow, velocity pressures are extremely low. And if you've done much pressure measuring, you know that measuring extremely low pressures is difficult. So what almost all of these probes will do is amplify that velocity pressure signal. So the only difference between one pickup to the other, some of them amplify it differently. And, go ahead.
One I asked over at CFE, we had one box that I think everybody's worked on. The duct guy shoved the duct too far in there,
Mhm.
and it pinched the tube inside there. You can't get it in there. They tried to move it out, done much different things. I don't see why we can't just add an aftermarket one a little further down the duct and call it done.
Now, if the hoses are clogged, it won't read.
Okay. Let's say this is our supply duct coming into it. Right in the inlet here is usually, sometimes it's out here. The duct would come all the way out to here. Right here is where that cross flow sensor is, then our damper, then the reheat coil on down the line. Somewhere out here is the main trunk. Okay, and we're tying on to the main trunk. We can put that anywhere out here after it tees off this main trunk. We just gotta make sure that we're far enough away from this takeoff or any elbows that we're not gonna get bad airflow, bad turbulence. So yes, we could move that, just abandon that one in place, buy an aftermarket one, maybe put it right in here. You can go out here, let's say, here's your T's going off the discharge side. You could put it right here also. Okay? The problem here is that this ductwork may be bigger than what's over here, so your velocity pressures are even lower again.
You know which one I'm talking about, don't you?
Oh, yeah.
But that cold restrict airflow too.
No, airflow's airflow.
It wouldn't change the velocity at all?
No. The only thing that's changing the velocity is the size of the duct. Okay? If you're putting 100 CFM here, it's got to come out over here. It may do it at a lower velocity or a higher velocity, but it's still going to be the same amount of airflow. Discounting any leaks or anything. So yes, that is possible. You just want to make sure that everybody's aware that you've used a different sensor, because in that TEC there's a place where you factor in that amplification. And if you mess with our TEC as much, you'll know that's the flow coefficient.
Do those aftermarket devices, is there something in their paperwork to tell?
Yeah.
What range it does?
Yeah, it'll tell you what the amplification is. That's not as critical though as if you have a balance man come balance it, he's gonna put the flow coefficient in there correctly. Because even if I know that flow coefficient, that amplification, the balance man's still gonna tweak it up or down just a little bit to get it as close as he can. Okay? The weirdness is that you're gonna have 1,000 VAV boxes with a flow coefficient close to one number, and then one with a flow coefficient that may be totally different. And it's correct. Okay? So that'd be the only caution if you're going to a different, airflow sensor.
That was brought up a long time ago, just changing out the cross flow. I don't know why we didn't do it.
You don't always necessarily have a good place to do it over here or over here. Sometimes those branches come off right at the
That
discharge.
one's got a long trunk.
If it's got a long trunk, then we might.
That's in a sterile corridor or a sterile area. And it's a big ordeal to get in there now.
So that might be an option. Okay. these dash lines here just show our air tubes that we run down to this airflow sensor. And there's a static pressure, differential pressure transmitter built into this box that actually reads that velocity pressure. Next thing down the line here is our reheat valve and actuator. We're normally going to supply that reheat valve, and we're going to put an actuator on it, tie it back to the TDC, it's ready to go. Again, every actuator has the possibility of having different motor timings. We've got to know that to make sure we're putting the right motor timings in the box, in the TDC. Optional, but we like to see it, supply air temp sensor. This gives us a troubleshooting tool to let us know what the air temperature leaving this box is. Okay, it normally ties back in right here on this, yeah, right there where it says TCD2.
Hey, Thomas,
2, it's 3.
Tap up.
Type of.
can you explain how the mixed, or the heat water valve and the damper modulates whenever it's a DO?
Okay, you've got 2 DOs for each one. Okay, DO1 and DO2 both control one motor. DO3, DO4 both control the other motor. These motors are, they used to call them stepper motors. I don't know if that's a proper term anymore or not, but you put power on them one direction. You got 3 terminals that come out. You put power 24 volts on one set of on one set of wires. That motor's going to drive one direction. Just like similar to, you know, the way you used to be able to take a DC motor, and if you reverse the polarity, it runs a different direction. Okay, these are AC motors, so it's not the same, but the same logic applies. If you put power on one side, it's going to rotate one direction. If you put power on that other wire, it rotates the reverse of that. Okay? Now, I know that it takes that motor 90 seconds, let's say, to drive full open to full close. So if I turn that one DO on, the one that makes it open, for 10 seconds, I've driven that motor 1/9 of the way open, I guess it's that. Okay, if I turn the other DO on for 10 seconds, it closes right back. And that thing is precise enough that it knows that, you know, if I've been on for a second and a half, I've moved so far. And on a 90-second motor, you basically have 1 second per degree. And so if I want to go to 45 degrees, I run it for 45 seconds. If I want to move back the other direction, 10 degrees, I turn the other DO on for 10 seconds. And it just keeps up with that through the day, and it knows I've ran this far so long, I've run this direction so long. And so it knows where it is, and you can look in that controller and see its position at any time. Now, does it get off every now and then? Maybe so. And so our controllers are designed, the default, once a day or twice a day, they run those motors all the way back to 0. If it's a 90-second motor, it may run it for 100 seconds, back to 0, so that it knows it's zeroed out again. At that point, then it starts over fresh, and it starts opening up, and it knows where it is again. Does that help?
Just recalibrate the settings.
Yes. Okay. So the little valve actuator is the same way. It does the exact same thing. And when the TDC calibrates, it runs it back to 0 also. Since you asked that, if we put on these, when we have rooms where we cannot close that damper because of airflow requirements, and we install what we call auto zero modules, at that point we never zero this actuator again. So that if it's, you know, after 6 months in operation, it may be a little lost. It says it's wide open, but it's not. Okay? So they've come up with a sequence in here on how to adjust for that. And basically all it does is it looks at the airflow. It says if I'm not at full airflow, but my damper is wide open, it just arbitrarily drives that motor into the open position, open direction for like another 10 seconds, trying to get it wide open. Okay, which if you have a 90-degree rotation, that's fine. If you have a 45-degree rotation, now you got the potential for screw-ups. Because if it drives past that 45 degrees, trying to open farther, what's it do? Just starts closing off. Okay? So if you've got an auto zero module on a VAV box that has a 45-degree rotation, you have to put mechanical stops in that actuator to keep it from overdriving at the 45-degree mark. Okay. Now, that takes care of all the hardware. In the logic, what are we doing? This is a sequence, again, that came from an engineer, so it's a little different than what actually happens in our CAN program. Our CAN program basically is going to look at the room temp, compare it to the current set point, and depending on whether you're using the set point dial or it's daytime or nighttime, the current set point could be various different values. Okay, but it's going to compare that room temp to the current set point. It's going to modulate this damper for cooling between a minimum and a maximum that we have set in this controller. So if we set that the minimum is 100 CFM, the maximum is 1,000, it's going to set a flow set point somewhere between 100 and 1,000, and then that damper is going to modulate reading this airflow in order to maintain that CFM. So the damper does not modulate to maintain temperature. The damper modulates to maintain airflow. The controller then adjusts the airflow set point to maintain the temperature. You see the distinction there? The damper is not directly controlling the room temperature. Its job is to maintain airflow. Then the controller is telling it how much airflow to actually maintain. If then these tubes pull loose or give us an incorrect, this cross-flow sensor gets plugged up and gives us an incorrect reading, what's going to happen? If you're lucky, the sensor will show failed in the controller. Because if it shows failed, then it reverts to what's called a pressure-dependent control, and it'll control the damper directly to maintain temperature. If it doesn't fail, if it's just giving you the incorrect reading, this thing may just go wide open and stay there if it's not reading enough CFM. Say it's supposed to have 500 CFM, but you're reading only 200, but it thinks that's a good reading. It's just going to drive the damper wide open and stay there, whether it's in heat mode or cool mode. Okay? So it's imperative that we have a good airflow reading.
If you don't have an airflow, some type of airflow sensor, where is that considered pressure dependent boxes?
Mm-hmm. And it'd be a different controller. Okay? This is a pressure independent controller. Okay? And what that means is that the airflow through this box is going to be maintained regardless of the static pressure in this ductwork. Okay? The airflow is independent of the static pressure. Pressure dependent, we won't measure this. Okay? We'll just open and close that damper in order to maintain temperature. But the amount of airflow that goes through that box is dependent on the static pressure at the inlet of that box. The higher the static pressure, more airflow we're going to get. We have no way of limiting the airflow at that time. So that's the difference between pressure dependent and pressure independent. Almost everything we do nowadays is pressure independent. And It gives us a lot better control. It gives us, a warm fuzzy feeling. We know exactly, pretty close anyway, how much CFM is going into the room. But it puts in another source of confusion and something else that can go wrong. Okay? So now, we're controlling this damper, we're modulating this damper to control this airflow. In our normal, out-of-the-box control scenario, we're going to modulate between a minimum and a maximum for cooling. Then we're going to drop down, for heating, we're going to drop down to some minimum flow in heating. It can be the same as the cooling flow minimum, or it can be different. But once it switches to heat, it's going to go to that setting, that minimum, that whatever the heating flow minimum value is, and it's going to stay there. It's going to modulate that damper all day long to maintain that 1 CFM. And then it's going to modulate this valve in order to maintain the room temp. Okay? You got one loop that's going to sit here and maintain airflow, another loop that's going to maintain the room temp by modulating the valve in the heating mode. Does that make sense? Now, several of our engineers now are wanting us to modulate in the heat mode also. They want us to modulate this airflow in the heat mode. And we can do that. We just change the settings in the TEC. Now we can make that damper open up, back up to some maximum heating at the same time as the valve's opening up, or we can let the valve go open first and then start opening the airflow up for heating, or maybe go the other way. Maybe have the airflow go up first and then start opening the valve. That would not work very well, but it is possible to set it up that way. That gives the engineer the ability to put that box down to an even lower minimum CFM, even in the heat mode, and still only bring that volume up if he needs to in order to maintain the room temp. Okay? So we're starting to see a lot of that. Especially, they did a lot of it at UMS. Okay? Any questions on those basics there? This one over here, this is just VB cooling only. Everything's identical, only now we got rid of our reheat coil. Okay, so now we're in a space that we've decided doesn't need any auxiliary heat. And so we've gotten rid of the reheat coil. So now it's even simpler. All we do is modulate between some minimum CFM and some maximum CFM in order to maintain room temp. And that's it. Does nothing else.
How come the SAT didn't wire it up on that one?
Hey, folks.
Needs to change it out.
Yeah, let's draw it on there. Actually, maybe they're smarter than we are. They know that if there's no reheat coil,
Wireless, yeah.
yeah, it's wireless. They figured out that since there's no reheat coil, the temperature right here should be the same as what's coming out of the air handler, and they already know that. Actually, I don't promote using these if there's not a reheat coil. To me, it's just almost a waste. Okay.
Still selling.
Yeah, I mean, okay. The salesman in front here said we can still sell them,
Right.
which is cool.
That's not happened before.
So this setup is just the same TEC, the same everything. We just don't have reheat coil. Now I can do the same thing with. I can take this drawing right here and do constant volume hot water reheat. Everything here would be identical for constant volume hot water reheat. Okay, the only difference in the logic is that this airflow set point It's just gonna be the same all day long. It'll always be in the heat mode. We'll just be putting out a constant volume of air through here all day long, and our temperature control will be right here with the reheat. Okay, we're still measuring the airflow. It's just all that we're changing inside the TEC is the CFM settings work to a different drummer. I mean, they're doing something different at that point. Now, for Siemens, be cautious though. The constant volume applications aren't in the same TEC as the VAV applications. So you don't just take one and make it the other real easily. And if somebody calls for constant volume, it may be a different TEC part number. Again, pressure dependent. If we wanted to be pressure dependent, we just take this out, use a different TEC. We don't have the airflow control. This damper then just modulates fully open, fully closed in order to maintain the temperature in the space. We no longer know what the CFM is. We can't control to some minimum CFM. Done correctly, they'll probably put some kind of mechanical stop or just clamp that actuator down on the damper to where it cannot close all the way. Because very few rooms do you not need some, fresh air moving through it all the time. Any questions on any of that? For us, these TECs are great. They're beautiful, but all you got to do is mess up one setting in them, and you've messed it up on several boxes. It'll cost us a lot of time. So you've got to be real careful when you're setting these things up. And if you're setting them up, you don't know exactly what you need to put them in there. Just ask, because it can take a lot of time to go back and change that after the building's occupied. Depending on what's wrong with it. And there can be up to 99 points in these devices that you're scrolling through when you're setting them up, trying to get them right. Some of them are obvious, some of them are given to us from the mechanical drawings, some of them the balance man helps us with. But if we, one thing I also like to always mention is that if you've got one brand of VAV box on a job, and they're all identical VAV boxes, just different sizes, then your flow coefficients ought to all be real close to the same number. If the flow coefficient for one of them is supposed to be 0.68, they ought to all be real close to 0.68. So if the balance man goes through and he tries to give you a flow coefficient of 1.2, you question it. There's something wrong. Okay, either somebody entered the wrong duct size, or there's leaks somewhere, but it shouldn't be 10% above or below that standard number. If you come up with one that's 0.2, that's a problem. So you've got to question those things. It's going to cause us problems in the future.
On those flow coefficients, can't you only change that thing one time, and that changes the default rate until you load it in on the front end?
No, not really. I mean, you can change it as many times as you want to. The problem is if you change it one time and you do upload that to the main controller,
That's what it's going to say.
the main controller then has a value stored in it. If you go back then and change it at the TEC, plug directly into the TEC, and you don't update the controller, then after the first power failure, the controller is going to send down that incorrect value. Okay, so there's two different philosophies on how to do that to keep that from happening. One of them, you do all your changing in the TECs and you never update anything at the controller, the main controller, until everything's done. It's all exactly the way you want it. Then you go build your TEC points in the controller and upload them. And you don't ever change them again. The other philosophy is you install them, do your changing, and update it every day. If the balance man is on the job at the end of the day, when he leaves, you go update it, so it's always got the latest information in it.
Also, if you update every day, it's like trashing.
If you update it every day,
No.
depends on what they meant by. Now, by update, I mean that the controller is pulling the information out of the TEC and storing it in the field panel. Okay? If you're going the other way, if you're commanding stuff in the TEC every day, that double EEPROM does have a life to it. You can only write them so many times, but I mean, it's like in the tens of thousands of times that you can write them before they're bad. So that shouldn't be an issue, you know, for most stuff. Now, I could write a program that would write it, you know, every second, and that would become an issue. But I just have to hear what they were talking about when they said that. Okay, that says 750, that says 755. I guess we'll regroup on Tuesday.